Okay, so this solution video is one of three for energy conservation, and this one jumps around just like one of the other ones did. We start off on page 93 with number 1, number 3, and number 6 down here, and we jump to page 94 where we have number 13. There's 13. Then on page 95, 17 to, go back, 17 to 21. So there's 17 through 21. Number 24 and 26. 24, there it is. And 26. Then on page 96, we have 29 and 31 to 36. So 29 and 31 through 36. Next page. Oops. 36. Okay, let's begin at the beginning with number 1. We have a rock that's falling. They give us the mass, they give us the change in height. That is enough information to solve for the gravitational potential energy, and so it asks for the kinetic energy. All right, let's take a look. All right, so the trick with these conservation of energy problems is like you kind of hit a roadblock. So, all right, we're looking for kinetic energy, and we know that the formula for kinetic energy is 1/2 mv squared. And we have the mass, but we don't have the speed. Now, we can take this as a kinematics treatment. So yeah, this is, what is it, a rock? It's a rock. Rock's dropped off a bridge, so V initial is 0. It's freely falling, so acceleration is due to gravity, negative 9.81 meters per second squared. Its displacement is the same as the change in height, which is 90 meters. Make that negative because it's displacing downwards. We're solving for VF. Do VF squared is VI squared plus 2AD. VI is 0. The negative on acceleration and the negative on the displacement cancel each other. Don't forget to take the square root. We get a final velocity of 42 meters per second. Stick that into 1/2 mv squared, and we get a final kinetic energy of 883 joules. Now that was a pretty quick treatment because that's not actually the way I want you to do it. Even though there was a way this time of actually solving for that velocity, sometimes there's literally no way of getting yourself out of this. It's like doing 1/2 mv squared and you literally have no idea how to solve for v. That's okay, because that's not the strategy I want you to think about. Instead, I want to think about the whole notion of conservation of energy. We have total energy before, something happens, like a rock is dropped or somebody jumps or whatever, something happens. Total energy before is total energy after. And that's the total energy is the potential plus the kinetic plus any work that was done. Now, most problems are not going to have work kinetic and potential energy, work kinetic energy and potential energy both before and after. Usually it's one form of energy becomes another form of energy. Let's keep it simple. But you have to consider the problem to think about what types of energy that is. You have a rock up on a cliff and then the rock falls from the cliff. So when the rock is in that elevated position up on the cliff, that would be gravitational potential energy up there. There's no kinetic because it's at rest. There's no work being done. Nobody's actually like doing FD or pushing on this rock. It's all gravitational potential energy, and that gravitational potential energy becomes the kinetic energy as it falls. So not only this like kind of vague arrow thing, it is literally equal to gravitational potential energy before equals kinetic energy after. Point being, if I can't solve for the kinetic energy because I don't know the speed, so technically if that k equals 1/2 mv squared doesn't work, then see if you can solve for the energy that it becomes or that it came from. So in this case, I can't solve for kinetic energy because I don't know the speed. So if I can't solve for the kinetic energy that the rock gains from falling, I can solve for the gravitational potential energy it had to begin with. mg delta h that it had to begin with is the kinetic energy that it gains. Now I know m, I know delta h, I can throw g in there, and I can solve for my kinetic energy. When we do 9.81 times 90, we wind up with, oh, will you look at that, 883 joules. That's what we got before. But before, we used kinematics to get our answer, and this is not a kinematics thing. We want to treat it as an energy treatment thing. So in the end, we wind up with 883 joules. And 883 joules is not actually the answer because I did not read carefully. In fact, the displacement is not 90 meters, it's 20 meters. The cliff happens to be 90 meters high, but the vertical displacement is only 20 meters. I feel like these questions are a trap. I fell into that trap. Let's fix my math. All the way back to the beginning of the problem, delta H is not 90, it's 20. I could start this whole thing over, but my explanation and what I just went through is still completely legitimate. I'm not going to erase all that because none of that is wrong. I just made a math mistake. So I still want to redo the kinematics treatment. So now my vertical displacement is not 90 meters, it is 20 meters. Okay, with my new vertical displacement of 20 meters, I have 196 joules of kinetic energy coming from the kinematics treatment. Let's look at the energy treatment. This 90 joules now becomes, this 90 meters now becomes 20 meters. If I do 9.81 times 20, what I wind up with is 196 joules, which is what I had before. So again, the principles stay the same. I just messed up the math. My bad. And just underlines the point about how careless mistakes happen to everybody. Even when you know what you're doing, if you don't read carefully, you're going to mess it up. And then finally, the answer says approximately, what is your answer? 200 joules, which is choice 2. Now, I just spent almost 7 minutes doing one problem, but I wanted to explain to you the background of how these conservation of energy problems work. And show you that if you do it another way, you still wind up with the same answer. But we already did free-fall kinematics a long time ago. I want to focus on energy right now. Let's move on. Okay, so 3 says we have a constant force is pushing a block on a horizontal track at a constant velocity. Right, so this right here, in terms of the energy, a force is being applied, which means that work is being done. Also, it's moving, so that means it's being displaced, and there has to be displacement for work to be done. Also, the force and the displacement can't be at right angles to each other. That's why something in uniform circular motion, no work is being done there because force and displacement are at right angles. Anyway, so we know that work is actually being done. Now, it's a horizontal track, so that means there's going to be no change in height, so there's going to be no change in gravitational potential energy. They also mentioned that it's a constant velocity, so if there's no change in v, then there's no change in the kinetic energy. It's not gaining speed, so it's not going to gain kinetic energy. So then, all right, let's see what else the question asks. As the block slides, there could be an increase in what? We just said that there's no change in gravitational potential energy, so that knocks out choice 1, and it knocks out choice 3. We also know that there's no change in the kinetic energy because it's not speeding up or slowing down, so that knocks out choices 3 and 4. So the only increase is going to be internal energy. And then internal energy is pretty much synonymous with heat. So there is work being done. There's energy added into the system because you're applying a force over a displacement. There's definitely work being done. There's definitely energy being added to the system. But with no change in gravitational potential energy, there's no change in the kinetic energy, and there's also no springs involved. There's no changes in those guys. Where is the energy going? It has to be going to heat. So there would be internal energy, and that's choice 2. Okay, number 6 is very similar to number 1. You give us the mass of the ball being thrown upwards. You give us the initial kinetic energy of the ball on its way up. And they want to know how high does it go. Well, height does not relate to kinetic energy. Height relates to potential energy. So the kinetic energy before equals down at the bottom when it's thrown equals the potential energy after at its highest point. So this means I can use that kinetic energy to 25 joules and stick that in for the potential energy and then solve for a delta H. We wind up with 5.1 meters, which is choice 2. All right, let's jump to 13. So in 13, we have a graph of energy versus distance, and it has the kinetic energy increasing steadily over time, and it has the gravitational potential energy decreasing steadily over time. over distance really, but it's also over time. And then the sum of the two is constant. Now they refer to this as total mechanical energy. Mechanical refers to motion. So if they're saying anything is mechanical, they are saying it relates to motion energy. Give me a dot there. And total mechanical energy is equal to the sum of the potential energy plus the kinetic energy. And we say if there's no friction, the total mechanical energy is conserved. So yeah, as the displacement goes on, as this object moves, what is it talking about? A moving block. So as the block moves, the kinetic energy increases. It must be speeding up. The gravitational potential energy decreases. That would be PEG specifically, not just any old potential energy. PEG. And that decreases, and the sum of the two is constant. So it must be losing height and gaining speed. Maybe it's falling. There's one flat surface. No, because there is a change in height. Moving upwards. No, because the potential energy is decreasing. So not choice 2. Choice 4 involves constant velocity, which is not true because the kinetic energy is increasing. So the speed must be increasing. So 13 is choice 3. It's falling freely. It's losing potential energy, so it must be losing height, but it's gaining kinetic energy, so it must be gaining speed. Falling freely fits that, so 13 is 3. Okay, 17. So reading through the problem, first of all, I see horizontal surface and constant velocity. So with a horizontal surface and a constant velocity, I know my gravitational potential energy and my kinetic energy are not going to change. So then it says the work done against friction produces an increase in what? Well, work leads to energy, because work is energy. Work is not weight. Work is not a force, so it's not choice 1. Work is not momentum, so it's not choice 2. Work could be potential energy, but I just said that the potential energy is not changing, so it must be internal energy or heat. Here we go. Next. All right, so we have a bank of problems, 18 through 21. So we have a driver in a car making an emergency stop on a straight horizontal road. So if it's stopping, I know the speed is going down, and it's a horizontal road, so there's no change in height. All right, so lowered kinetic energy is going down, but the gravitational potential energy is constant because the height hasn't changed. I see rubber on dry asphalt. The car is sliding or skidding, so that rubber on dry asphalt, I remember from friction, I can look up the coefficient of kinetic or moving friction and I get a mu of 0.67. So I noted that, and that might come in handy. The car skidded for 16 meters and the mass of the car is 1,200 kilograms. Now 18 wants the weight of the car. We just do a simple weight equals mg and we get 11,772 newtons. So 19 wants the friction force. I know that's mu times the normal force. Thankfully, I looked up mu already. I had a feeling I would need it. Now, normal force, remember, on a flat surface, the normal force equals the weight. So that 11,772 that we got for the weight, we can put in for the normal force. It gives us a friction force of 7,887 newtons. I'm not rounding for sig figs, whatever. Yeah. I mean, if you want to round for sig figs, looks like I have 2 sig figs maximum, so 18 would be 12,000 newtons, and then 19 would be 8,000 newtons, or 7,900 newtons. Anyway, 20 wants the work done. I know that W is FD. Work in this case is done by friction. That's why they asked you to find the friction force. So I will put in the 7,887 newtons and the distance it went, which would be 16 meters along the ground. And so we get 126,000 joules, not newtons this time, but joules of work done. Now, you might be asking yourself, what does any of this have to do with conservation of energy? That is where number 21 comes in. And it says, assuming energy is conserved, calculate the speed of the car before the brakes were applied. Well, how the heck can you get that? Well, the car had kinetic energy when it was moving, and the kinetic energy, remember, reduced. Why? Because work was done to stop the car. Kinetic energy before the braking was done is equal to the work done to stop the car. That eventually becomes heat. It heats up the brakes. But that didn't ask about the heat. The work done to stop the car, I just figured that out. That would be the 126,192 joules. So I can put that in for kinetic energy. Now, why would I want to do that? Kinetic energy, we know, is 1/2 mv squared. I know the mass, I know the kinetic energy, which was the amount of work that was needed to stop the car. If it has 126,192 joules of kinetic energy, that is exactly how much work you need to do to reduce the kinetic energy to 0. In other words, stop the car. You wind up with a speed of 14.5 meters per second. Again, don't forget to square root because the v is squared on 1/2 mv squared. Alright, so like I've said about questions like this before, would this be a great regions question? You betcha. Would it be a great review question for the regions? You betcha. Would I put something like this on the work energy test? No, because most of this actually does not have to do with energy. And like I said, I try to focus the tests on the topic at hand without getting too far afield. Anyway, the next one is going to be 24. So 24 says the direction changes, but the speed's constant. What else is constant? Well, if my direction is changing, then anything that's a vector will also change. Velocity and momentum are both vectors, so they are out. And displacement is a vector, and you could say, well, can't you change your direction and not actually displace? However, we are moving. Like we are actually moving. So if we're moving, you're going to have a displacement. You will be displaced. So displacement is not constant. But kinetic energy is a scalar that depends on mass and speed. So if the speed is constant and the mass is constant, what else is constant? The kinetic energy, choice 4. 26, this says a ball is falling freely. What happens to the total mechanical energy? Well, let's remember that the total mechanical energy is the sum of the kinetic energy plus the potential energy. And so as a ball falls freely, falling, your potential energy is going to decrease because you are losing height, and your kinetic energy, because height decreases, and then the kinetic energy is going to increase because the speed increases as you fall. But the sum of the two, one becomes the other. The loss of gravitational potential energy, it becomes the kinetic energy. So kinetic energy, potential energy is lost. Where does it go? It goes to the kinetic energy that's gaining. But the sum of the two is constant during friction. So 26, the potential becomes the kinetic as the ball falls, but the sum of the two is constant, choice 3. To see a graph of what I'm talking about, see number 13. Okay, so 28 and 29. 28 we already did previously. You have a force versus displacement graph. You take the area under the curve. But 29 says, boy pushes the wagon. What happens to the wagon's energy? So let's read the description. And the problem says that we have constant speed and we have a level sidewalk. So if that's the case, constant speed means there's no change in kinetic energy, because there's no change in speed. And then the level sidewalk means there's no change in gravitational potential energy, because there's no change in height. Doesn't let me make dots. I don't really understand that. Dot there. And so then what happens to the wagon's energy? Because work's being done. We have a force times displacement. So work is being done. And so if work is being done, where is that work going? If not into potential energy or kinetic energy, it must go into internal energy in the form of heat. So yeah, the internal energy increases, and that would be choice 3. And the last set of problems for this video is 31 through 36. So 31, we have this guy lifting something using a pulley. For 31, it wants to know what's the change in gravitational potential energy as compared to the work that's done. Let's take a look at the work that's done. The work is FD. We have 600 newtons worth of force being done, and the displacement would basically be how much rope is being pulled. 3 meters of rope is being pulled. And you can say, wait, isn't 3 meters the vertical displacement? Yeah, but in order for the crate or box, or whatever that is, crate, in order for the crate to be lifted vertically by the rope, 3 meters of rope have to be pulled. There's only one pulley wheel there. There's no trick going on here. So 3 meters going up, that's 3 meters of rope pulled. So the force is being applied over 3 meters. So the person did 1,800 joules worth of work. But let's look at the gravitational potential energy change for the crate. And so even though 1,800 joules of work are being done by the person, the actual net change in energy, the gravitational potential energy change, is only 1,472 joules worth. And so the difference, that's 338 joules less. The gravitational potential energy is 338 joules less. There's probably a rounding error there saying 330. But yeah, it's definitely going to be less by 330 joules, choice 2. You might say, well, why isn't it the same? Where does that energy go? Well, maybe that pulley wheel is not totally efficient. And if you're going to lose some energy, you'll lose it because of friction, and that energy will go to heat. Okay, number 32. Got a block on a horizontal tabletop, slowing down, and it comes to rest. What happens to kinetic energy and internal energy? Well, it's slowing down, so the kinetic energy is going to decrease. And it's a horizontal tabletop, so there's no change in height, there's no change in gravitational potential energy. And so if there's no change in potential energy, then if the kinetic energy decreases, where does it go? It goes into internal energy. So the pendulum's swinging back and forth. When the pendulum hangs straight down, the pendulum's at rest. And we would say that's the 0 displacement. And then when it swings at its highest point, that's the most height, most gravitational potential energy, and most displacement from the rest point. So if you had, as the displacement increases, as the pendulum displaces from its rest position and gains height, the gravitational potential energy increases. So that's choice 4. I just don't like the graph that they chose. That graph basically says that if they put 0, they didn't say where they put 0. 0 for that graph is actually in the middle. Here's what the graph should actually look like. That's really what the answer should look like. So that's choice 4. All right, so 34 to 36, we have a roller coaster situation. It's no surprise that C is lower than A, because with any actual roller coaster, you're going to have some friction, and you're never going to get back up to the height of the first lift hill without some help. Sometimes they have like a chain drive that'll do work to lift you up there. But if you're just using gravity, friction is going to slow you down bit by bit, and so the hill is going to get smaller and smaller. Anyway, 34. Find gravitational potential energy up at A, that's mg delta H. 63,765 joules. If we round for sig figs, that would just be 64,000 joules for 2 sig figs. 35, find the speed at B. Well, down at B, it's all kinetic energy and no gravitational potential energy because it loses the height, but that's where it's fastest. So if I want to know the speed at B, I can use the kinetic energy because the kinetic energy at B is the potential all the way up at A. So I know the potential at A, so let's do 1/2 mv squared equals the potential at A, which was the answer to 34. Work the math out, you get 19.8 meters per second. Don't forget to take the square root because V is squared. And the last problem in this video, the last problem in this set is 36. Compare total mechanical energy of the car and passenger at points A, B, and C. The one thing to recognize, because I was like, oh, C is a lower hill, there must be friction. The problem specifically says neglect friction. There is no friction. 36 has a short answer and a little bit longer answer. First of all, the short and simple answer is that the total mechanical energy at A, B, and C is the same. Total mechanical energy, which is, we know, kinetic energy plus potential energy is the same at A, B, and C. Now, to be clear, just to illustrate that a little bit more, at A, it's all gravitational potential. Highest point, and there's no speed. So there's no kinetic energy. Then at B, it's all kinetic energy because it's fastest there, and there's no height there, so the gravitational potential energy is 0. And then finally at C, it's both. Gain a little height, so you gain some potential energy, but I can imagine that it's still moving at C because it hasn't gotten back up to the level of A. So it's maybe slower at C, it's slower at C than at B, but it still has KE. But the sum of the two of them, the potential plus the kinetic, is the same for A, B, and C. Let's see if we can get, there we go. All right, and so yeah, the actual answer to the question, what it is looking for, is right here. Total mechanical energy is the same, and just remember that total mechanical energy is the sum of kinetic plus potential. All right, so this is video 1 of 3. There'll be 2 more, so stay tuned.